Here's a type of equation that you can solve using a substitution. It's called a Bernoulli differential equation, and here's the general form of it. dy dx plus some function of x times y is some function of x times y to the n, and if n is 0, then this equation is separable, and if n is 1, then it's linear. So this is really only interesting if n isn't 0 or 1. And back in the early days of calculus, people did a lot of just trying things out to see what would work, and someone, I don't know who, Bernoulli probably, stumbled upon this substitution. It turns out that taking u to be y to the 1 minus n turns this into an equation that we can solve. So let's use this substitution to solve this differential equation, x squared times y prime plus 2xy minus y cubed. You can see, comparing these general forms, right, the y to the n term must be y cubed, and so for us, n is 3. So we're going to do the substitution u equals y to the 1 minus 3. So u is going to be y to the minus second power. Okay, so now we need to figure out what is the derivative of u with respect to x. And this is, right, we have to do the chain rule here. So this is minus 2y to the minus third times dy dx. Okay, but right, we're ultimately going to use this to replace this y prime right here. So let's solve this for y prime, for dy dx. We get minus 1/2 y cubed times du dx equals dy dx. Okay, so now we can do the substitution, and something that I notice is, right, we have this equation that gives us u in terms of y. In principle, we would use this to get rid of the y here in the y cubed term, but that's going to involve some sort of weird exponents. But I'm going to want an over y cubed right here to cancel the y cubed that's going to come out of y prime when I do the substitution. So let's divide everything here by y cubed. So we get x squared times 1 over y cubed times y prime plus 2x, and then y over y cubed, that's y to the minus second minus 1. Okay, now let's do our substitution. So we get x squared times 1 over y cubed times y prime, and that's over here, minus 1/2 y cubed du dx, plus 2 times x times y to the minus second, but y to the minus second is u. Minus 1 equals 0. Okay, now we can simplify this. So the y cubes are gone. We get minus 1/2 x squared du dx plus 2xu. And then I'm going to move that minus 1 to the other side, so it's a plus 1. You can see that doing the substitution has turned this equation into a linear equation. And now that it's linear, we know how to solve it. Let's see, we want to find an integrating factor, so I guess the first thing to do is multiply by whatever we need to get this leading coefficient to be 1. So let's multiply this whole thing by, let's see, minus 2 over x squared, I guess, is going to do the job. So we get du dx, and then distribute this. So when we distribute that over to there, it cancels the minus 1/2 and the x squared. When we distribute it to our u term, we get minus 4 over x times u. And then when we distribute it to the right-hand side, we get minus 2 over x squared. Okay. Now p, right? P is our coefficient function on the linear terms, so or the order 0 term. So p is minus 4 over x, and our integrating factor is e to the integral of p. So e to the integral of minus 4 over x dx, that's e to the minus 4 natural log x. And remember, we don't need a constant of integration when we're finding our integrating factor. And doing a little algebra, this is x to the minus 4th. Okay, so there's our integrating factor. So we need to take, sorry, not that equation. We need to take this equation and multiply both sides by the integrating factor, x to the minus 4th. So we get x to the minus 4th times du dx minus 4 over x to the 5th, so I've combined some powers there, times u equals minus 2 over x to the 6th, I guess. Okay, now continuing on our usual strategy of solving linear differential equations, this left-hand side ought to be the derivative with respect to y of the integrating factor, x to the minus 4th, times u. And just a quick check that it actually is. So derivative of u times x to the minus 4th, that's there. And then u times the derivative of x to the minus 4th. Yes, we got it. Okay, equals minus 2 over x to the 6th. Now we can integrate both sides with respect to x. On the left-hand side, the integral and the derivative undo each other. And we're left with x to the minus 4th times u. And on the right-hand side, we get, let's see, minus 2 times, so minus 1 over 5 x to the minus 5th, I guess. Let's just check with the derivative, minus sign, that cancels, yes, plus a constant, of course. And now finish solving for these minus signs cancel. Finish solving for u. So multiply both sides by x to the 4th. So u is 2 over 5 x, I guess, when we multiply by x to the 4th. That leaves 1 power of x in the denominator, plus c times x to the 4th. Okay, so that's u. But remember, u was y to the minus 2nd. And so y is u to the minus 1/2. So y is 1 over the square root of u. So 1 over the square root of 2 over 5x plus c times x to the 4th. Okay. So the substitution u equals y to the 1 minus n, it always turns a Bernoulli equation into a linear equation. The resulting linear equation can still be sort of a mess to solve, but it does always work.